All right, so in the last lesson we learned about separable equations, so let's investigate a different technique that will address other types of equations. Okay, so let's say we've got a linear, let's say we've got a differential equation of this given form here, and we're going to define this to be a linear equation in the variable y. And so what we can do with this is if we divide by that leading coefficient out front, so that a sub 1 of x, we can get it into this other form down here, a little bit of variable manipulation, and that's kind of our goal for this lesson, is how do we solve differential equations in that form. So we refer to that form as standard form. Of a linear equation for these differential equations. So what would we consider then to be linear? And so I've kind of got two illustrations here. So the first one are linear and separable, so that we can use our separation technique from the last lesson. And the second example, this linear but not separable, this is where we need a new technique. Because I can't break up that y and x in terms of a product. There's a plus sitting there. So what do we do with something like that? All right, so I'm going to try my best to kind of walk you through why does this process work, and then we'll actually get into some illustrations, some examples as to what do you do first, what do you do second, what are the steps there. So let's start with the product rule, and I'm going to get some very well, let's just review the product rule here, and I'm going to use some interesting notation. So let's say I want to multiply u of t times y of t, and I want to take the derivative of that. Well, what would the product rule say that is? That says take the first times the derivative of the second. So that would be u of t times dy dt. Plus the second times the derivative of the first, which is u prime of t. So I'm specifically writing in that fashion for a sort of clever idea, but we're going to come back to this. So just a quick reminder, that's what the product rule says and does. Okay. So let's say we have a differential equation that looks something like this. It says we got a function dy dt plus u of t p of t times y equal u of t times g of t. Okay, so if you want to pause and just dissect that, let's just say we've got something like this, and we're going to create a y of t and p of t. So this part right here, we're going to claim that we're going to be able to rewrite that relationship as the derivative of u. So there exists some, that's a t there. There exists some set of functions, some combinations of functions that will do that. Okay. So if we can find that magic substitution, then we can rewrite that previous statement as u of t dy dt plus y prime of t of y times y equals u of t gt. Now, what does that remind us of? Okay. Remember I reviewed that product rule earlier? Well, that's where this little magic part's going to come in. So that expression that I've got written there is just an illustration of the product rule. So I can then substitute in this u of t, y of t, okay, so let's then integrate both sides here. So give myself a little space here. So if I integrate u of t, y of t prime, and integrate this other side. Right. Well, if I integrate something that I differentiate, oh, sorry, both of these are dt on that. Sorry. So if I integrate an expression that I'm differentiating, that essentially cancels that out, and I'm left with the original notation there of u of t, y of t. And now this other integral expression, not too much I can specifically state about it other than hopefully it exists. And then if I want to solve for y, then all I got to do is divide both sides by that y of t. And so I have a function contingent upon that I can find an integral that we haven't necessarily seen an example of yet, divided by u of t. Okay, so assuming I can do that process, I can find that integral, then in theory we'd be good to go and we could go forward from here. So as we look at why this process works, and you ask yourself, well, why does it work? The answer is it works because of an illustration of the product rule. And so now this hypothetical question of, well, how can I pick these magic u of t's and p of t's, like where are we going to get that from? Well, let's go through that. Let's go through how we would make that decision and what do we do with it. Okay, so that magic thing that we're looking for, we refer to as the integrating factor. So, question is, how do we pick a u of t? Well, we pick one that has this format to it. So it is e raised to the integral of p of t dt, or in general, the x case. So u of x equals e integral p of x dx. And so that function there, kind of scroll down here, so that p of x that's been sitting there floating, that is the thing that we're going to use that's going to allow us to solve this type of differential equation. So what are the steps involved? Now, real quick, let me make a quick subtle comment here. I don't expect students to necessarily remember the derivation of this process, like why does this process work. Beyond that, it is an application of the product rule, and so because of a clever choice we are making, we're picking things that are going to make the product rule be relevant and come out for us. So let's go through the general steps, and like I said, hopefully when we get into an example, that'll make a little bit more sense for us. Okay, so the steps are: make sure we've got it into the standard form for a linear differential equation. Number two, from the standard form, identify p of x, and then find the integrating factor, so that's e raised to the integral of p of x dx. We don't have to worry about constants at that point. Then step three, we briefly saw that when I ended up dividing by a term in the derivation phase, but step three is going to be multiply both sides of the standard form by the integrating factor. The left side is going to give us an application of the product rule, and hopefully the right side we're able to integrate on our own once we've got that simplified and figured out. And then step four is integrate both sides and then do our best to solve for y at that point. So I don't necessarily want to call this a disclaimer. I just want to, this is sort of a mathematical, keep an eye out for these types of situations. So because this process makes the assumption that we're going to divide by some function, we do have to have a conversation about watching out for things that'll make that function equal 0, because when we're dividing by that function, solutions of that division could be a domain restriction of some type. Okay, so except in the case in which the leading coefficient is 1, rewriting the equation in standard form will require division by a sub 1 of x. Values of x for which a sub 1 of x equals 0 are called singular points of the equation. Singular points are potentially troublesome. So if p of x is discontinuous at a point, the discontinuity discontinuity may carry over to solutions of differential equations. So again, when we do an example, we'll have a brief pause and go, are there any domain restrictions we need to be aware of because of that step where we divided? The transient term of the differential equation is a term such that taking the limit as t approaches infinity, that term tends to 0. A non-transient term tends to be constant and called a steady state term. So if you think back to a previous lesson, merely just measuring behaviors around a potential solution as to whether it's a steady state or something else. So we just refer to those as transient and non-transient terms.